Welcome to Lesson 12E, Practical Application of Oblique Shocks. In this lesson, we'll discuss a practical application of oblique shocks, namely compression of air at the inlets of supersonic aircraft jet engines. We'll discuss various engine inlet designs, such as those listed here, and this will be entirely qualitative. By way of introduction, consider a supersonic jet with an inlet to the engine at this location, where it's flying supersonically. The problem is that at the engine inlet, for most engines, you need subsonic flow into the compressor. Therefore, you must slow down the flow before entering the compressor. And as you slow down this flow, the pressure increases, which is actually a good thing because the compressor doesn't have to compress the air as much. There are several ways to do this. We'll talk first about a round inlet with a center body. This is a round geometry where we have a cone aligned with the inlet flow, which has Mach number greater than 1. The cowling of the engine inlet is designed such that the oblique shock that forms here impinges at the leading edge of this cowling. This is a weak oblique shock, and for the case of a round cone, it's also conical. Well, as we've been discussing recently, this oblique shock will reflect. In fact, it will reflect multiple times, getting weaker and weaker, till finally you have a nearly normal shock with a subsonic Mach number going to the compressor. These are all weak oblique shocks, where the pressure keeps rising across each oblique shock. If we let angle beta be that of this initial oblique shock, you can see that beta gets larger and larger, approaching 90 degrees through all these oblique shocks. A good example is the SR-71 Blackbird. In that aircraft, the cone, or what we call the center body, can move forward or backward to adjust to changing M inlet.
That's very impressive engineering.
That's for sure, Mr. Palpatine. In my opinion, the SR-71 is the most amazing aircraft ever designed. I note that as we go through all these oblique shocks, pressure goes up and Mach number goes down through this series of oblique shocks. And we can achieve a large percentage of the total required compression before the flow even enters the compressor. It's a great application of utilizing oblique shocks. Here's a picture of the SR-71 Blackbird, and you can see these cones at the engine inlet. My heart beats a little faster every time I see this amazing airplane. It flies so high that the pilots can actually see the curvature of the Earth. I note here that if the center cone is not at the proper location for the given Mach number, a bow shock forms here. They say then that the engine is unstarted. That's why you can adjust the cone location in and out so that this oblique shock will hit right at the tip of the cowling and then have several reflections as I drew. The F-104 Starfighter is similar in design, but it has half-round inlets with half cones instead of full circles like the SR-71. Here's a close-up of that inlet and the full aircraft. The F-111 Aardvark has quarter-round inlets, which they affectionately call armpit inlets, and adjustable wings. Here's a picture in subsonic flight, for example takeoff and landing, where the wings are not swept. But at high-speed supersonic flight, these wings are swept back mechanically.
Why do they sweep back the wings?
Well, first of all, note that this sweep back occurs only in supersonic flight, where we get a conical oblique shock from the nose of the aircraft. If these wings were not swept back, but instead looked like that, you would have lots of problems with the interaction of this oblique shock with the wing. And by sweeping it back, the entire wing is within the downstream portion of the oblique shock.
Thank you, sir.
At high speeds, the flow downstream of the oblique shock is actually subsonic, and the drag on these wings is substantially reduced when the flow is subsonic rather than supersonic. Here's a close-up of this so-called armpit inlet with the quarter cone here, and you can see a little bit inside this engine inlet here. Another way to do this is with rectangular inlets that are asymmetric. For example, the F-15 Eagle fighter plane. In that case, the cowling is asymmetric, with the upper portion more forward than the lower portion. Again, for a supersonic inlet, we get an oblique shock that again reflects several times, as previously discussed, until you get a nearly normal shock with subsonic flow into the compressor. The F-15 has an adjustable flap on the cowling to ensure that this oblique shock hits the lower cowling and doesn't bypass it. If the oblique shock bypasses this lower cowling, you would have supersonic flow going into the compressor. The adjustable flap serves the same purpose as the adjustable cone on the SR-71, but this flow is nearly two-dimensional instead of round. Here are some pictures of the engine inlets in the F-15. As you can see, this flap can be adjusted. During pre-flight inspection, the pilot will sometimes put one flap down and one up. They say that the pilot winks. You may have wondered before why the engine inlet was shaped in this way, with the front more forward than the back. Well, now you know. The more modern F-22 Raptor also has rectangular inlets, but with nearly horizontal asymmetry, which you can see from this picture, and there are some S-shaped ducts inside this inlet instead of flaps, and those are designed to reduce the radar signature of this aircraft. Here are some shock diamonds that we discussed previously earlier in the course. Here's a research aircraft from the 1960s called the XB-70. It also had rectangular inlets with horizontal asymmetry, but they have a common center, a common vertex. This aircraft was designed for Mach 3 cruising, and the oblique shocks are similar to those of the F-15. The Concorde was a commercial rather than military aircraft. It had 4 engines with vertical asymmetry and variable geometry as shown here, with the 2 engines on one side sharing a center vertex here. This was a very cool aircraft, but it was extremely expensive to fly supersonically. It's no longer in service. A third design is curved compression ramp, CCR, or diverterless supersonic inlet, DSI. The principle is similar to the others, but instead of a cone, for example, this design has a cusped inlet geometry. This portion is called the shoulder, and the upper part of the cowling is shaped something like this. In this design, there's not an initial oblique shock, but instead, for supersonic inlet, we get a series of compression waves that interact with each other and eventually form a nearly oblique shock here, which then reflects, and from then on it's a similar thing to previously, with a nearly normal shock and a high-pressure subsonic flow into the compressor. The advantage of this design is that, as you may recall, these compression waves are nearly isentropic, so the pressure rise is much more efficient because of the compression waves. Here's a picture from this website showing the swept forward cowling and the 3D gradual compression surface or shoulder, as I was describing. There are only a few aircraft that utilize this design, one of them being the Chengdu J-10B from China, which is shown here, and the US YF-35 Joint Strike Fighter, which has a DSI inlet, as you can see here. All of these are cool applications of compression waves and oblique shocks. And now you have a better understanding of why you see some of these strange geometries at the engine inlets. Thank you for watching this video. Please subscribe to my YouTube channel for more videos.
1, 2, 3. That's all there is to it.